Okay, we'll go ahead and get started. So you took your Module 1 exam, and now we're getting into Module 2. This is chapters 13 or 14, something like that in the textbook. I'll have to update those links in Canvas since I don't think they directly work from the module itself. So you have to go to the sort of course materials link to get into the textbook and see these. But now we're going to start talking about how do we figure out structure using spectroscopy. Spectroscopy is the interaction of light with matter. So we're going to look at a couple different analytical techniques to do that, see what data we can get out, with the goal of learning how to think about what that data is telling us, and then how these different instrumental techniques are telling us different pieces of the puzzle that we're going to fit together. One quick thing, I have to end today at 11:45 due to a meeting I have at 12, so we'll cut just a little bit short today. Any questions before we get into it? So in Module 1, we learned about how to communicate structure primarily through the line drawing convention. So you know that these molecules are composed of different elements. They have different bonding patterns. They can be neutral or they can have charges based on if there's an excess of bonds or a deficiency of bonds. And all of that relates back to the periodic table, how we count electrons and fill atomic orbitals. And so through the bonding patterns, we realize that molecules can have different functional groups, and that's a specific set of elements with a defined bonding pattern. So spectroscopy, as I said, is the interaction of light with matter, and what we're going to learn is how those techniques tell us about the functional groups present. The three different techniques, mass spectrometry, so MS. Notice that word is a little bit different. Spectrometry, it's not exactly spectroscopy, so it's not related to light as IR or infrared and NMR, nuclear magnetic resonance, are. So MS, IR, and NMR are the three techniques, and they're all telling us different things. And so from the data that they're telling us, we're able to get sort of these fragments that we can put together and make a structural claim. So we're going to learn, how do we directly interpret the data, what is there? But also alongside that or concurrent, when you're looking at the data, what's not there? That's equally as important because then you can rule out certain functional groups. And that will increase the confidence of what you're claiming a structure is. And the big picture of that is, organic reactions often produce more than one product. So if you have these products, two or more, maybe they're constitutional isomers, but maybe they're just totally different. How do you absolutely prove what's the major versus minor products present? So I like to lead this off by this slide here, learning to learn. So this is where we're really going to start to think and problem solve. So again, you can read a lot of the factual material in your textbook. And what I'm going to do is convey how do we manipulate, use it, and apply it. So metacognition is the ability to think about your own thinking. So if you're claiming something, does everything you know, does it obey like the rules that you've learned? So if you're making a structural claim, but a piece of data doesn't fit with that, you have to think, okay, something's wrong, so I need to revise it. But you have to be cognizant or aware that something's wrong. Heuristic, perfect is the enemy of good enough. So in problem solving, you're never going to get it right the first time. You always have to take that first step. So don't be afraid of failing or proposing something that, you know, could be wrong. You just got to take that first step, look at it, think about it, revise as necessary. But if you're in the situation where you're like frozen, I don't know where to start, that's not a good way to approach these. Sutton's Law. So Mitch Onstead, a reporter, asked Willie Sutton, who is a bank robber, "Why do you rob banks?" And Willie Sutton replied, "Because that's where the money is." So if you look at that sort of short dialogue, the reporter is probably asking more of maybe a deep or sociological or psychological question. And the answer is the money's there, so I'm going to take it. And so that's what is relatable to this. There's the data. How are you interpreting it? And that relates to Woodward's aphorism, or in science we call it Occam's razor. When you hear hoofbeats, think of horses and not zebras. So what is the most obvious thing that the data is telling you? You don't want your mind to run amok and start making up these really fantastical scenarios. Like, what's the simplest explanation is generally the truth. And then my favorite, Hemingway, all the symbolism is shit. So, you know, the shark's a shark, the fish is a fish, that sort of thing. I mean, very, very simple interpretation of what these things are. So today we're going to focus on mass spectrometry as the piece of information that is going to help us figure out molecular formula. And then from that, we can get degrees of unsaturation. And then we'll transition into infrared spectroscopy. That data shows us what functional groups are present, or if in a certain region there's not a signal, then that functional group is not there. And then we'll end the module on nuclear magnetic resonance, which will give us the uniqueness. It's going to tell you the unique number of carbons, the unique sets of hydrogens, and their ratios. So conceptually, you've been exposed to that already, but now you'll see the data. So I'll talk about this more in the coming lectures, but spectroscopy is really the science way of imaging. You can see, like, there's water in this plastic bottle. Like, you see the bulk liquid. But what you don't see are like the individual molecules, the actual bond connections. So spectroscopy is our way of imaging, like a dental x-ray is a way of seeing if a tooth has a cavity, or an MRI. So MRI is magnetic resonance imaging. That's just where the instrument, you are the sample. As a human, you're going into the instrument and it's looking at soft tissue. So it's seeing something different than an x-ray will. So that's what all these techniques are doing. We're just seeing different things. So we'll start off with this thought problem as an introduction to mass spectrometry. So given the mass or molecular weight of 86, so there's a clue. How do we determine the molecular formula? So we want the molecular formula for an alkane. So that's another clue. So what you don't see on this slide is any sort of structure, right? So how do you convert the number 86 into a molecular formula that's an alkane? So we basically have to find out what N is. And it has to obey what we've learned for an alkane, CnH2n plus 2. So we know because it's an alkane, it's a hydrocarbon, we're only dealing with C and H. But as we get through this exercise, you'll see it gets a little bit more complicated when there's those heteroatoms in there. Then there's other things we have to consider. So what's our first step? How do we go about this? So within that number 86 are all of the carbons and hydrogens for an alkane. So to get started, we can say, what is the max number of carbon atoms? And you'll see this is an iterative process. We're not going to get it right on the first go-round. We know that 86 has all the C and H's. So let's divide by 12. That's the atomic mass of carbon. And so that's going to get us an approximation of how many carbons there are, the N number. So when you do that, you'll find that you get about 7. And we're only going to deal with integers here. So that would come out to 7. And to find for the number of hydrogens that remains after we account for 7 carbons, we would take 12 times 7, and that would get us 84. And so the remaining amount of hydrogens has to be 2. So we could then therefore propose that C7H2 could be a molecular formula. But now, does that obey the CnH2n plus 2? It doesn't. So we see that our first iteration of this is wrong. And so now we have to revise it. But we've now put a boundary on the maximum number of carbons. It can't be 8. So 8 times 12, that's 80 plus, 16? That's 96 or something. 96 would be well above the mass of 86. So we're not going to go higher. We're going to go lower. So at 7 carbons, we see there's not enough hydrogens. So we're going to remove 1. So 7 minus 1 equals 6. Now is the max number of carbons. That should be a C. So then 12 is the atomic mass of carbon. We multiply that by 6 and we get 72. So the carbon contribution to the 86 is 72. The hydrogen count is then 86 minus 72, and that would get us 14. So therefore, we could propose C6H14. Then we could plug that back into the CnH2n plus 2 and say, okay, that obeys that rule. So that could be a molecular formula for an alkane.
Sorry, where did the
So we saw here in our first iteration, we divided by 12, we got 7. That sort of is the upper limit. We can't go to 8 because we're surpassing the given mass. So we have to we're just going to reduce it by 1 each time. So if we wanted to block this in, 7's too high, 6 is right on. What do you think about 5? If we used 5 carbon atoms and you went through that same process. It would have too many hydrogen atoms. So remember that for the n number of carbons, the max number of hydrogens is 2n plus 2. So if this was 5, the maximum number of hydrogens would be 12. But if you went through this math and you put 5 in, 5 times 12, you'd get 60. So 86 minus 60, that would give you 26 hydrogens. And so now you've bracketed the correct answer. So it has to be that molecular formula. And as we saw in the module 1, from this molecular formula, you could draw a linear constitutional isomer. Or you could start drawing branched constitutional isomers. So within the molecular formula, you have these different other claims, and then that's where things like the uniqueness, so the carbon and proton uniqueness that we'll learn in NMR will come into play. How do we further funnel it down into what is the actual structure? Any questions? Yeah.
Could you use 12n and then add 2n plus 2 equals 84 to just solve for n and go straight for the carbon instead of trying to bracket it? If you have your n carbon.
Did you try that? Does it work? I've never done it that way, but. Yeah, so I mean, again, that's perfectly reasonable. I'm not going to say that's going to work for everything, but it most likely works for alkanes. You'll see that when we have other types of masses, so this mass is even. So it's not going to hold for everything. You know what I mean? You just have to be aware of that. So to recap our thought process here, the alkane tells you that there's only C and H present. So you're dealing with atomic masses 12 and 1. Because it's an alkane, there's no degrees of unsaturation. That was the CnH2n plus 2. And then we just did this first approximation about figuring out the max number of carbons, dividing by 12. That gave us 7. We found there were not enough hydrogens because we got C7H2. And that's the metacognition part. That doesn't obey the CnH2n plus 2. So it's telling you have to do a revision. So to further illustrate why it doesn't make sense, if you plug that C7H2 and figure out the degrees of unsaturation, you end up with 7. And here's a proposal for 7 degrees of unsaturation. And that's a pretty wild proposal when you look at it. It has 6 pi bonds in 1 ring. One of the reasons it's kind of funky So these highlighted carbons, what hybridization were they? So the carbons of a triple bond. So sp. And do you remember what geometry an sp hybridized carbon should have? Linear. But you can tell by the way it's drawn in that ring, they're severely bent. So if it's supposed to be linear and it's bent, that's abnormal. And when we learn module 3, once you start deviating away from the normal geometry, that induces strain. And things don't like to be strained. The analogy that I use is like, you know, it's about lunchtime, and if you haven't eaten yet, you're going to be hungry, you're going to be mad, you're going to be strained. So the molecules don't like to be strained, you don't like to be strained. So those are things you have to look out for. So because 7 was our maximum, we just methodically removed or reduced it by 1 to get 6 and went through the same exercise. That left us with, so N equals 6. Now we have the 14 hydrogen atoms. And then we said C6H14. That fits nicely into the CnH2n plus 2. And then we bracketed it by going down 1 more to 5 to really boost our confidence that it has to be 6. And as you see in the table, these are the 3 attempts, 1, 2, and 3. We're decreasing the carbon count each time and then revising the hydrogen count. And the key thing is here, it has to have no degrees of unsaturation because it's an alkane. So 7 carbons has 7 degrees of unsaturation. It doesn't obey it. 6 is the Goldilocks scenario. The porridge is just the right temperature. It's not too hot. It's not too cold. And 5 is just, I think we can agree, ridiculous. I mean, you should be able to understand from what you know of carbon bonding that 26 hydrogens is just way too many. So it's a ludicrous claim here. And so we ended up with C6H14. Any questions? And so now we're going to sort of kick it up a notch, as M2L Lagasse says. We're going to add some spiciness to it, because now we're going to start considering heteroatoms in there. So C and H is pretty straightforward, but when you put these heteroatoms, you have to think a lot more about what functional groups they can be in. So remember, you learned all these functional groups with oxygen, these functional groups with nitrogen. And to demonstrate the thread of this thought process, I'm going to give you the structure here first. And this is testosterone. And it's a steroid. So steroids are hormones, which are small molecules that signal a biological process to start, continue, or stop. So like when you go through puberty, your hormones hit and changes happen. Those changes happen from these small molecules like this. So the question is, this is the way we're normally used to doing things. You see the structure. We're going to figure out the molecular formula, calculate the weight, all of that. But the thought experiment is, if you didn't know the structure of testosterone, if you were just given the mass, could you find the molecular formula and then propose the structure? And you'll see it gets increasingly difficult once the heteroatoms are in there. So you're given the structure, you do some C, some H, and some O counting. Obviously, since this is organic chemistry, there's a lot of C's and H's. Can you eliminate any response based on the heteroatom count? So we can eliminate A because it says there's 3 oxygens. And when you look at it, you see there's 2. So that's a cheap way to eliminate one of them. Now here's a more subtle question to you. So you have B, C, and D. Of those 3, is there a way you could eliminate 2 of them, just sort of looking at the molecular formula itself? Remember when we were determining degrees of unsaturation from molecular formula? And we said oxygen does not change the hydrogen count. If you think of the implications of that statement based on the formulas you can see, does that help you eliminate any? So see these numbers here, 31 and 29. How would you describe those numbers?
They're less than like 2 times the carbon count, so
So they're odd. And so it's sort of getting to what you're saying. You can't have an odd number and divide by 2, because 2 is your definition of a degree of unsaturation. So one of the subtle hints here is that the hydrogen count, because you do not have or you do not have halogen or nitrogen, the hydrogen count must be even. So C is the correct answer. But you could go through, count the carbons, count the hydrogens, count the oxygens, you'll end up with C. So let me just make a note. So with those odd ones, you can't divide it by the H2 because you're not going to get an integer. So 192802. So let's review using the molecular formula to calculate the weight. So carbon, that's atomic mass 12. Hydrogen is 1, oxygen is 16, and then we just put in how many there are. We'll do the easy stuff first. 12 times 19. I'm sure there's some fast way to do that in your head, but just punch it in here. So that gets us 228. And then we add all that together. and that gets us 288. So our answer is B. So really that's what mass spectrometry is doing. It's giving you the mass of a compound. So now visually, when you look at it, how many degrees of unsaturation are in testosterone? So we have 6. We see we have 2 pi bonds, and then 1, 2, 3, 4 rings. That gets us 6. So you can do it visually, or you can use the molecular formula to calculate that number 6. So in relation to the 2 oxygen containing functional groups, do you remember what their names were? Say it again. So ketone and alcohol. And this is specifically a secondary alcohol. So visually you see that. Both of those functional groups have oxygen. The oxygen's in different bonding patterns. So infrared spectroscopy will tell you that those 2 functional groups are present in the molecule. There are certain signatures that are going to say this signal belongs to a carbon-oxygen double bond, and this signal belongs to an oxygen-hydrogen sigma bond stretch. Visually, you'll see it. That's like analogous to a dentist looking at a dental x-ray and say, I see a little spot here, that's a cavity. I recognize it's abnormal, we have to do something about it. So the IR is telling you, hey, I have these 2 fragments. They're somewhere in that molecule. So this one is A. So has anyone ever seen the data for a mass spectrum? That's what you're seeing now, so handful of people. So let me explain like what you're looking at. You saw the structure of testosterone. We're able to calculate the C, the H, the O count. We know how to calculate molecular weight from it. And what you're seeing in terms of the data now is a mass spectrum. So on the x-axis, it says M divided by Z. M means mass and Z means charge. For the purposes of our discussion in this class, in this course, the charge is typically 1. Whether it's +1 or -1, it's just 1. So really you're looking at the mass. So the red lines you see coming off from the x-axis, those are the signals. And the signals correspond, as you increase from left to right, they correspond to the mass of the ion, either the plus or the minus ion. The y-axis is called just relative intensity or abundance. It is how often are you seeing that mass present. So the way you want to interpret these mass spectra, it's really from the right, the highest mass, and then looking backwards towards zero. We know that the molecular weight of testosterone is 288, and it's kind of hard to see, but this number right here is 288. So that mass corresponds to the molecular formula of the compound we're looking at. Since it's an ion with all of the elements of the molecular formula, it's called the parent ion. And it's given the nomenclature you see, a square bracket with the capital letter M. The little plus there, that just indicates the charge. So the instrument, you make a sample, you shoot it in, it's going to spit out that mass of 288. But what about all these other masses that are lower? So essentially, those result from fragmentation. The molecule it's charged now, it's higher energy, it's going to degrade into other little bits of smaller mass. And that's what you see with all the other lines. There's a peak at, I think it says 124. It's kind of tiny. That's called the base peak, because when you draw a line over to the y-axis, that's the most abundant peak. It's the tallest peak there. Those are two of the main things you have to look for in these mass spec data. The parent has all of the elements of the molecular formula, and then the base peak is the most abundant peak. In all of the rest of these little clusters here, you see there's a lot of these little clusters. Those are called daughter ions. So the daughter ions result from the parent. And one thing I want to point out, when a question you could ask is, why are there so many? You know, if you look at any individual cluster, in this cluster right here, there's, I don't know, 5, 6, 7, 8 little signals. Why are there so many? The reason for that is, for any particular element, as we'll see, that element can have isotopes. And so we'll review what the definition of an isotope is and how it affects the way this data looks. So the question is, given the mass spectral data of M to Z equal 288 for testosterone, is there a way to calculate the molecular formula C19H28O2? So now pretend you don't even know what the structure is. You're just given this number, 288. Can you figure out what is the molecular formula, and then ultimately, what is the structure? The reason that we can do this really lies in the isotopic abundances of carbon, oxygen, and hydrogen. So to understand why this is possible, we'll have to review what an isotope is. We'll look at the elements of interest in what their ratios of isotopes are and how we can use that to our advantage. So an isotope of an element, and this is the nomenclature here, the isotope of the element E has the same atomic number Z, but the mass number A differs due to a different number of neutrons. So the number of neutrons is Z minus A. The nomenclature you might be familiar with if you've heard of like radioactive carbon dating. So like carbon-14. The majority of carbon in life is carbon-12. So that's typically the nomenclature you'll see. And so this number would be 6, just to put it in that sort of format. So those are isotopes. Carbon-12 is the most abundant. Carbon-14 is a radioactive one. And as we'll see on the next slide, isotopes are present naturally in different amounts. And those different amounts will affect the way the mass spectrum looks. So here are the elements we're interested in for organic chemistry. So again, Z was atomic number. So hydrogen has 3 isotopes. So its symbol is 1H. Here's the mass. Notice there's a lot of digits after the decimal. And that will matter because it helps to give a more precise answer through mass spectrometry. And then the last column there is showing you the abundance. So if you take all the different isotopes and you add all their different abundances up, it'll equal 100. So we see that hydrogen has an abundance, it's greater than 99%. So the remaining 2 isotopes, deuterium, which is given the nomenclature 2H or just the letter D. Notice the mass increases, and it's less than 0.1% abundance naturally occurring. And then the little yellow and black propeller there, that's the radioactive symbol. So tritium 3H or T now has an atomic mass of 3. And the stars mean that it's not appreciably present naturally. It's made sort of synthetically. So carbon, atomic number 6, has 4 isotopes, or excuse me, 3. Carbon-12, carbon-13, and carbon-14. Carbon-14 is the radioactive one. And then you see, starting from carbon-12, the mass increases by 1 each time. So carbon-12 is 98.93% abundant. Carbon-13 is 1% abundant. That 1% of carbon is going to be really important to us because we're going to revise that exercise we did at the start of the lecture. We just plugged in 12 to figure out the maximum number of carbons. Well, it turns out based on this ratio here, this 98.93 to 1.07, we can use those to our advantage, stick some numbers into an equation that will give us the actual value of carbon atoms present in a molecule. So we don't necessarily have to go through an iterative process. We can just plug some data into an equation. It's going to say, okay, it's this many carbons exactly. So unfortunately, I didn't get through all this slide. I have to wrap it up to go to this meeting. But we'll continue with this on Wednesday, where we start looking at the different ratio of these isotopes and their signatures. By signatures, look at bromine and chlorine specifically. So we'll look at some data and you'll be visually able to tell if those are present in a molecular formula.